Hello everyone, welcome to the fourth lecture of week 10. So we have started discussing about quantization for language models, and we will continue this discussion in this lecture also. So we talked about one of the ingredients of QLoRa. We will talk about the other two ingredients, the double quantization and paged optimizer, and then we will see putting it all together. How does the final training through QLoRa looks like? So quick recap. So when we said what are the major innovations that QLoRa brings in, we talked about 4-bit normal float. So we will store all the weights in 4-bit through quantization. Okay. The other two innovations are double quantization and page optimizer, and this is what we will discuss in this lecture. Interestingly, we will talk about later on that you will store the main weights, the pretense weights, in 4-bit storage data type, and whenever you have to compute with the weights, you will dequantize those to B float 16 type. This is a special data type mainly for ML operations called brain float 16. And it's different from AP16 standard data type. It's mainly built for ML operations. Okay. So let's talk about the other two ingredients, double quantization and page optimizer. So what is the idea? So remember what we are doing through quantization. So suppose this is my original weight tensor. We have a constant. What is the constant? Like if you want to convert these weights to int 8-bit integers, I'll take the apps max here and say 127 divided by apps max, right? And then I will multiply the weight with this constant. So this is my constant, CFP32. So I rescale all the parameters using this particular constant, and I get the corresponding integer after rounding. Okay. So something like I go from here to here. Now, do you see any problem with this approach? So think about all the weights that you have, right, in your model, and you find the absolute max and then quantize using that. 127 divided by apps max becomes the constant, and you multiply each weight by the constant. Right? What can be the problem with this? So how do the weights look like, right? I mean, see, there is no bound to the weights. The weights are around mean 0 variance 1. But some weights here and there can go and become very, very large, right? So maybe all the weights are around this, in this region, but some weight somewhere has become like 10,000 plus. So what is the impact? So this is what we call it an outlier. Suppose you have an outlier. What do you think will be a problem with this? See, the problem will be, I'll again go back and say 127 divided by, let's say 10,000, 10,000, right? This becomes a very small number. Let's say 0.0127, right? And now you multiply a weight like into 1.5, right? And then you do rounding. What do you get? I'll get 0. So maximum weights because of this will go to the same bin of 0, right? I'll not be getting many numbers in other bins because of this outlier, right? Which is expecting that the numbers are uniformly distributed. I mean, so they would be roughly in all the bins depending on this outlier, and this outlier creates a problem. And so I want to avoid these issues, right? So this if apps max is very, very high, it's just an outlier, this will create a bias in our quantization process. So how can we avoid this? The idea is that, okay, even if there is an outlier, you may have very few outliers like that in your entire weights. So what we can do, rather than having a single constant, what can we do? We can do something like a block-wise quantization. So that is, we don't take all the weights together and do quantization, but we divide the weights into some blocks and do quantization individually for each block. And this is what is called block quantization. So for example, let's take this weight tensor again. This is a 5 cross 5 weights, 25 weights. So previously what I was doing, I was finding the absolute max here, and this can be an outlier, and because of that quantization will have a huge problem. But now suppose I divide into blocks of 5 each. Okay, so you flatten this matrix and you divide into each block of 5 weights. Okay, and now you run the quantization independently on each of the blocks. So that means I'll find the max here, and I'll do whatever 127 divided by max of block 1. Let me write it abs max, absolute max, even if it is negative, doesn't matter. So like that, I'll do 127 divided by abs max block 2. So even if there was an outlier in one of the blocks, it will only impact the quantization in that block, right? Will not impact other blocks. And that's the idea. So outliers will not affect the quantization in the other blocks. So I can do independently these quantizations. Now the problem is, if I use a block of very large size, I will still have a very large block that is affected by the outlier, right? And if I use very small block size, right, what will happen? I will have to store all of these constants also in FP32. So that will become again very large number, right? So what do we do? So we'll talk about that. So let's say coming back to finding these constants, and we independently rescaling all the parameters. So this is the constant. So what I will do, I'll rescale the parameters. So this will use this parameter, this particular constant to store, right? And similarly, this will use this constant to store blockwise, and they are independent across blocks. So you see the constants are different across blocks. Okay, so you rescale all the parameters per block, and then you have a new array of FP32 values of these constants, right? Now this again takes some space, right? Because as we discussed, if you are using blocks of very large size, a very large block will be affected by quantization. So you use some medium sized blocks, but even if you use medium sized blocks, you will have quite a lot of such constants, right? And that can take a lot of memory. So idea is that, okay, I already have the idea of quantization, so why can't I do quantization over these constants again, right? So I quantize these constants again. So repeat the same process of quantization for these quantization constants, right? So again you find the abs max from here, and say 127 divided by that, and the constant, and you find you do the rounding, and you have your new integer to store these constants, right? And this is why this particular method is called double quantization. I first quantize blockwise. From each block I get a constant, and then I have an array of these constants. I do quantization again on these. Okay. So now what's the difference in the memory consumption for this toy example before and after quantization? So what happens before any quantization? So before any quantization, you had a weight matrix of size 5 cross 5, so 25 values, and you were storing in 4 bytes, right, 32 bits. So you needed 25 cross 4, 100 bytes for storing this weight matrix. Now let's see what happens if you do a single quantization, right? If I do a single quantization, the normal quantization we talked about earlier, then, and I'm using int 8, so each of the 25 values will be stored as an 8-bit integer, so you will need 25 bytes. Plus, I'll need to store one constant, right, in FP32. So plus one constant for 4 bytes. So I need only 29 bytes storage as compared to 100 bytes. It's a huge reduction, right? What is the problem though? The problem is that there may be an outlier and that may affect the quantization process. The error may be high for quantization. So I want to avoid that. To avoid that, I do block-wise quantization, and block-wise quantization will actually increase the number of bytes needed for storage, right? So now if I go to block-wise quantization, I have 5 blocks. I am still storing the entries as 1 byte, so I still have 25, but I have 5 blocks, so I have 5 constants. So 5, and those I am storing in 4 bytes, so they have 20 bytes for these constants. So 25 bytes plus 20 bytes, so you have 45 bytes. So you see, you have gone from 29 to 45 bytes to ensure that the outlier does not impact the entire data. That's where comes the double quantization. It says, okay, why do you have to waste 20 bytes for this? I can again quantize these 5 constants. So what will happen? So I have these 5 constants, I again quantize them. So I'll just need 5 bytes to store these, plus I'll have a constant of 4 bytes. So how much storage do I need? 25 plus 5 plus 4, 34 bytes. So you see, it's in between what you were doing with the normal quantization, 29 bytes, and what you would have done with block-wise quantization, right? So this is for double quantization, less than what you get in block quantization, and but it's greater than what you do in the normal quantization, right? But it has its advantage that now this outlier will not impact, right? Because see, even these numbers, the individual things that you are storing per block, they are not the max value, they are the 127 divided by apps max. So apps max comes in the denominator, so it will not be a large number that will impact the storage of these integers, these constants. Okay, so that's double quantization. So yeah, we went from 100 to 34, is still a huge reduction, roughly 70% reduction in the memory in this particular toy example, right? In the normal case, we go from 16 or 32 bits to 4 bits, right? So a lot of reduction that happens because of this. Now let's talk about the final third ingredient of QLoRa. So why do we need another ingredient here? So see, this is needed because of a very particular problem that always happens when you train large language models, right? So whenever you have a neural network, the one problem that you face is running out of memory, right? So what do we do? Why do you run out of memory? Because at one place you have all these memories, the state memory, you have the gradients, you have the parameters, you have the optimizer variance, momentum, right? And sometimes you do mixed precision, so you store a master copy of the model weights in addition to what you are computing with. At the same time, you have activations, right? You have activations of all the layers, and that again can take a lot of memory. So and we do something to avoid this, right? And what is that? Let's understand. So suppose you have a simple neural network that has some layers, and given the input, you compute the output. So when you do forward pass, you are computing activation at each of the layers, right? You compute activation at layer 1, layer 2, layer 3, right? Now, if you have to continue storing this activation, it takes a lot of memory, and that's where you can go out of memory. So what has been seen, it's easy for the computers to recompute the things than to have it in the memory, because what the computers lack are the memory, and they are very good at processing. So they can do this trade-off that you forget, whenever a particular activation has been used and you have gone to the next activation, you can get rid of this, and whenever you need it during backpropagation, you can recompute it, right? So that's the idea. You don't need to store all of these hidden states. You can recompute whatever is needed. So we only store in memory whatever is needed at that point of time, and you keep discarding activations that have already been used, right? So you just keep on computing. You compute this, at that time you already have forgotten this, and also this, right? And when you compute this, you have also forgotten this activation. Now the problem comes in the backpropagation time. So because backpropagation again needs all the activations for all the layers, so you will have to recompute all, right. Now this, if you have to recompute all and you think about the number of layers, maybe say 50, 100, this will be a huge, it will take a huge time, right. So we do a trade-off again. We say, okay, let's not discard every checkpoint. So we have a lot of layers. So what we can do, let's we don't want to compute through all the layers. So at certain point in my so let's say I have some n layers. So what I will do, I'll find out some equally spaced layers where I will store the activations, right. And this is what we call as the gradient checkpoint. So that I have to do computation only when I go from here to any layer up, right. I can use this or down, whatever is needed. So I don't have to go beyond this block size. I don't have to traverse through n layers. And typically people say you have to do it for root n. You can do it in root n layers. So that means each block will be roughly root n size. That many computation you will have to do, rather than doing n computation for n layers. Okay. So you usually keep these checkpoints at every root nth layer, and assuming you have an n layer neural network. So when we recompute for backward passage, you don't have to recompute from the scratch, but you can start from the nearest layer for which the gradient has been checkpoint. So and this allows you to get rid of this out of memory error to some extent, right, but not completely, because this activation, as we saw, depends on many things, including the sequence length, right. So there may be some long sequences in the batch, and this may impact the memory that is being used, and it may happen you have some memory spikes in certain sequences that are very, very long. So what is done in QLoRa, you use some paged optimizer. So you also loop in your CPU. So while everything is happening in GPU, you use some paging technique. So what is paging? So it's a memory management method by which you divide your RAM into equally sized pages. Okay, and what is done in paged optimizer? So you enable page-to-page transfer between CPU and GPU. So whenever there may be a memory spike, what you would do? So you would say that, okay, I will transfer certain pages from GPU to CPU, okay, and then whenever the GPU has a space back and you need a particular page, you will move it back to GPU, right. So that's the idea, you avoid memory spikes through this. Okay, so these were the three ingredients. I mean, the main thing is the normal float for the data type, and that's where all the weights are stored. And the second one is the double quantization, that is again used for putting these weights, right. Otherwise it's quite similar to what you do in LoRa. So you will still have these two A and B matrices. These matrices are not quantized, because you see the main gradients and everything is happening in these matrices. So you don't want to convert them and again quantize and dequantize again and again, and these are only a very small number of parameters. This is where you have the largest number of weights, right, and that's where you want to save memory by storing them in NF4 data type, right. But whenever you need to compute, you will dequantize them back to BF16 and do your computation, but you will store always as NF4. So these pre-trained weights are stored as NF4. For forward pass, you will convert them to BF16 for computation. Okay, and then BF16 values of W, A, B are used, and you perform the computation. Okay, and you don't store these BF16 values of the computation. You just delete them, right? You only store them as NF4. Okay, and NF4 you already have a copy. You don't need to store another copy. These weights are not changing at all. So you just have one copy. You dequantize it whenever you need something and delete it. Right? That's all. Backward pass, anyway nothing goes through here, so that becomes easier. You just process through this BF16 weights altogether. So gradients go through these LoRa adapters. Okay, so putting it all together, you have, right, I mean it seems like for a 10 billion model you can just use say 12 GB of memory, and that generally works by using all these ingredients of LoRa, right. So pages will be moved from to the CPU from the GPU whenever you don't have a space, right. You will move it back to the GPU whenever it is required in the edge space. So mathematically what happens? So there is a scaling factor typically in LoRa. So you have the pre-trained weights plus you have B times A, and you do some scaling. Many papers have said you can even do this. So you can have a scaling parameter divided by the rank of the matrices, and you can also replace it by a single scalar S, right. So this is what you want to compute, right. So in forward pass you are multiplying it with some input x. So x w naught plus alpha by r x b a, that's what happens in the forward pass, right. Now remember, the only thing that is being stored as NF4 is w naught. So this one you have to dequantize to BF16. Everything else is already in BF16. Okay. So if you expand the formula, these are all easy, all in BF16. So you just take the values as it is. Only W naught you have to dequantize, and because it is double quantized, you have to double dequantized. Right? You are storing this particular constant, and you will have this weight. You will do double quantization, and you multiply with x, that is already in BF16, right. And yeah, you compute your values, and you don't need to store this double quantized value of the weight, right. You can delete it whenever your task is done. Okay, so this is about QLoRa. I mean, so how do you use this for ensuring that the language model has been trained through quantization aware training, right. And that is has become very popular for fine tuning large language models, where you may not have sufficient GPUs for doing even LoRa fine tuning, but you can use quantization aware fine tuning, right. And this book discusses this in some detail. So yeah, with that we will have another lecture where we will talk about some other aspects of parameter efficient fine tuning methods. Thank you.